But for now, we have Martin Hron, who's going to give a talk on the fresh smell of ransom coffee. So can we please welcome Martin to the stage?
Thank you. Hi. So welcome everybody to my talk. This is the last talk of a day. It has been a long day, so I'm here to entertain you a bit. And what could be more entertaining than a live demo that could possibly fail, right? So let's dive into the presentation. So who am I? Actually, I work as a security researcher at security vendor Avast. And to be honest, this talk is not my area of expertise. It's more like a personal story, because I love coffee. You've probably seen this. That's exactly the moment when you want to cry, right? This is a ransomware, and it's a well-known and big strain of ransomware called Wannacry. And you can easily spot what's wrong with your computer, right? Because if you see this, you are doomed. But what about devices that doesn't have any screen or keyboard, like IoT devices? There is a running joke that the S in IoT stands for security. And we will dive more into how bad the situation is, right? So as I said, I'm a coffee addict. I love coffee. So let me ask you a question. How many of you like coffee? OK. How many of you can't live without the coffee? We are developers, right? Most of us, IT persons. OK, so what do you think what happens when you deny a developer a decent cup of coffee? This could happen, right? It could be a crisis for the whole industry, right? What about like developers without coffee? That's going to be disaster. So that was the initial impulse, because I can't live without the coffee. So my idea was, let's research on coffee makers, particularly on smart coffee makers, because these devices are connected to the internet, to our Wi-Fi networks. And unfortunately, it's quite easy to misuse them. And I picked this one. It's called Smart Coffee Maker. And the smart functionality here is basically just to be able to control the coffee maker using your mobile application. So you have your coffee ready in the kitchen before you get out of a bed. That's as simple as it is. It's a really simple device. It has like 4 buttons, small display, nothing really fancy. On the technical side, when you take the device out of a box, it creates its own Wi-Fi network for setup, which is called Smart Coffee XX. And these 2 X stand for the last byte of the MAC address. So that's kind of a unique identification of the Wi-Fi for setup. It listens on the port TCP 208A1. That's the only port which is open. And it uses a very simple binary protocol without no authentication, no authorization whatsoever. So I was quite curious, like, what can you do even without connecting the coffee maker into your own network? Because that's the purpose of this setup network, right? And it turned out that you can do anything. It comes with the companion application, as I said, for iOS, for Android as well. And it's pretty simple. You can prepare your own formula for a coffee, like the strength, number of cups. And you can brew the coffee from the application. So that's as simple as it looks like. In terms of a protocol, this protocol has been already documented on the internet to some extent. And it's really, really simple. So the whole protocol consists basically of few bytes. The first byte is a comment, then followed by n bytes depending on the comment. And then there is like a terminator, which is 7E hex always. The response is very simple as well. So the response basically starts with the response type, then followed by n bytes of data again, and a terminator. So in case the response type is just a NAK or acknowledgement response, the response type is always 3. So that's the whole protocol. As I said, it has been documented on the internet. So you can find, for example, this command, which when sent to a coffee maker, it brews you a nice cup of coffee with the default settings of the coffee maker. So just these 2 bytes to port 2081. There is also one command, one specific command, which is like documented through only some extent. And this command is 6D. What it does, it turns the coffee maker into an update mode. And it looks like this. So once you send this command, the coffee maker switches itself into an update mode and waits for another comments. It turned out that all the documented commands didn't work in this mode. And I was quite puzzled what's going on, how should I proceed to get to know how the update process works. So I tried to use the application, because the application is able to update the firmware on the coffee maker. The problem with the application, or with my coffee maker, was that the firmware was up to date. So that wasn't the way to go. But something has changed. When the coffee maker is in an update mode, it changes its Wi-Fi network into Smarter Coffee Update XX. Again, XX stands for last byte of the MAC address. So I've tried everything. The only open port, again, is 2081. I've tried everything to connect the coffee maker, send all the commands to fuzz the protocol. Nothing basically worked. So how you should approach such a situation? There are actually, the easiest way is to get the firmware, because by reverse engineering the firmware, you can get the precise, let's say, description of the protocol and exactly how it works. So how can you get the firmware? There are, again, several options. One pretty obvious, Google it. That didn't work in this case. There is no firmware for this coffee maker on the internet. You can sniff the traffic between the companion application and the coffee maker. That didn't work as well, because the coffee maker was up to date. Next option is to dismount the device and download the firmware directly from the CPU or from the chip. That's kind of a tedious process, and I would like to avoid that. So the last option is to reverse the companion application itself. And because it's Android and it's an APK, it's pretty easy to do so. And it turned out, when you open the application itself, it has 2 very interesting files in it, in its assets. It has like binary file coffee.bin and binary file kettle.bin. It turned out that these are basically firmware images for all 2 products that the company does, which is a smart coffee maker and a smart kettle. So when you open the file, it's obviously unencrypted. Anybody knows what these strings are? So are typical AT commands used for modems, and in this particular case, it's basically command strings, or these are command strings for ESP8266 chip, which is the Wi-Fi modem, which is probably, or at this time, I really don't know what's inside, which is probably inside the coffee maker. I guess most of you know the ESP8266. If you are tinkering with the IoT, it's the most common Wi-Fi modem. OK, so I decompiled the companion application, which basically proved my point that the update process is the same for both products, and it only depends on a type of the device that's being read from the device itself. So it serves either the binary coffee.bin or binary file kettle.bin, depending on a type of a device. So let's have a look into a binary file coffee.bin. Like, if you have a firmware image, you need, like, the next step is probably to get to know what architecture is it intended for. Again, you have several options. You can guess. You can use some auto detection features, for example, for IDA Pro. But for me, because I like to dismount devices and eventually putting them together, I dismounted the coffee maker. That was the easiest option for me. So this is the whole coffee maker. Basically, this is the whole logic of the coffee maker. You can see there the ESP8266 chip, which is the modem. And after a while, I basically identified like 4 main components on the board. The one is, as I said, the ESP8266. Then the second, the number 2, is basically ARM Cortex M0, which turned out it's a brain of the whole coffee maker. And it's kind of funny, because this chip has like 64 kilobytes of memory. And comparing to ESP8266, it's way less powerful. It's like 10 times or 12 times less powerful than the actual Wi-Fi modem. But that's how it works. There are also like 4 debug pins or debug headers with the ports used for programming and also for communication with the modem. So you can basically, using these pins, you can tap into the communication between the modem and the main CPU. OK, so the next logical step is to get a data sheet for the CPU. That's how it works, right? And because I already knew what type of CPU is inside, I was able to load the file into IDA and started to decompiling or reverse engineering the whole thing. Usually, the easiest way how to reverse engineer some firmware is start with the strings, because that gives you a pretty good clue what these strings are used for. And by referencing them to a code which uses them, you can pretty fast get to main functions. And it turned out this is probably the most complex and the main function of the whole coffee maker. It's a big switch, and that switch is basically the whole handler for all the commands that the coffee maker is able to run. By proceeding further, this is basically just a close-up of this function. So you can see there are like already known commands, for example, 6D. I'm not sure if you are able to see. This is the 6D command, which is basically the start of the update. OK, so let's fast forward a bit. After 5 days, I was basically able to reverse engineer the whole firmware and get all the main functions. Like, it's easy because the firmware itself is like 49 kilobytes. So it's pretty small. It's a really dumb device. There is no fancy OS, nothing like this. And I came up with this architecture or diagram of the coffee maker. So you can see it's pretty simple. There is few detectors basically wired into the I/O pins of the CPU directly, which is like missing carafe detector. So when you take out the carafe, the coffee maker basically doesn't allow you to brew a coffee. Then there is a grinder motor, heating element, hotbed. Like, it's pretty simple. Control buttons. The only interesting part could be a coffee flap, which is basically the flap between the grinder and the filter, which opens at the moment when the coffee is ground. So, and 3 water level sensors. If you look at this picture, you can see there is no security measure in hardware. So every security measure in this coffee maker is in software. So once you change the firmware, once you patch the firmware, you can potentially create a really dangerous machine, which overheats, which runs the grinder forever, for example, which basically grinds the coffee forever, right? After a while, after reversing the component application, I was also able to identify the exact process of the update. And it turned out it's very simple. Again, no authorization, no authentication, no signature. The only thing is the CRC at the end. So it works basically like this. So once you switch the coffee maker into update mode, it changes the Wi-Fi network, waits for a start of the update, and then block by block, each of size 256 bytes, basically it uploads the new firmware into a coffee maker, following by CRC and the command which signal to a coffee maker that that's the end of the update. So it's pretty simple. So if you have the knowledge about how the coffee maker works, how the update process takes place, the easiest and next logical step is to try to update the firmware, right? So this is the first attempt I made updating the firmware. OK, to be honest, I've cheated in this case, because I've only replaced the image which says that there is no carafe, because there is no carafe. But, and it also turned out that there is no font in the coffee maker, so everything you see, it's an image. So there are like 12 images for cups, start, medium, beans, everything is basically just an image. So it's pretty easy to tinker with that. OK, so the next logical step is to create something more complex, right? So I've created a payload, because it turned out there is a space at the end of the firmware, which is freely available and could be used. So I replaced the original handler for a join to Wi-Fi command, which is kind of, like interesting. So you basically create a malicious payload that activates on a try of the user to join the coffee maker into his or her network. OK, so that's the time for the demo. Fingers crossed. And I will show you what I've created in 5 days. So if everything works, you can see the display of the coffee maker here. So that's my hand. And let's upload the payload. I don't know if you can see the terminal. Is it readable? So I've made a little application for that, because it's a tedious process. So it's called manual. Sorry. OK, I need to. Okay. So the first stage is to switch the coffee maker into update mode, which is basically by sending these 2 bytes. OK, that was pretty quick. So now the coffee maker is in update mode, the Wi-Fi changed, and it awaits the next command. So the next logical step is to upload the payload and the modified firmware. It sometimes takes a while, depending on Wi-Fi. OK, so that's exactly the case where something goes wrong. Here we go. Update completed. It should restart automatically. As you've seen, there is no interaction from the user needed. So everything was just automatic. So now the coffee maker restarts itself, and it contains the malicious payload. So the third stage, which I have here as a setting on fire, is basically to run the command or to send the command to a coffee maker to join to a Wi-Fi. And this is the outcome. It again takes a while, because it needs to change the Wi-Fi network again. It needs to connect to the other Wi-Fi. OK, sometimes. And this is how it works. And if you wait a while, it gets mad. I think it's like 10 repetition of these two images. So what it's now doing is it's heating up the element, but because there is no water, you can't see it. And now it runs the grinder and runs the grinder for forever, basically. So you can't use your coffee maker anymore. And so smells good. So the only thing I can do is unplug the coffee maker. And the other thing is that you can even change the command or override or patch the command that basically says update. So in that case, you brick the device, and unless someone like take it apart and replace the firmware using the debug port or the programming port, it won't work anymore. Okay, so that went pretty smooth. Well, actually, this is in case the demo won't work. And I can like quickly show you, oops, that wasn't what I wanted to show you. Okay, that was too easy, right? Come on, show me. Okay, let's fast forward to that part, which is here, I believe. Okay, let's hope it's going to work. If I fast forward, it has a nice steam effect when the water starts dripping through the coffee maker without the carafe. So it's just to entertain you even more. Okay, so this is just another case. Okay, so let's discuss the attack vector, how you can misuse this. Actually, this device, I don't know if you recognize that, if you have kids, and even the Lego Mindstorms, that's a smart brick which basically powers the whole Lego. I was able to create this version of uploader into that brick, so you can easily visit your neighbor who has this coffee maker. So obvious, there are like few versions of attack vectors. So the first one is man-in-the-middle attack, because in the new firmware, they actually added a functionality that needs the user to press update on the coffee maker. But if you think about it, because there is no authorization, authentication, the Wi-Fi is basically opened, it's pretty easy to do a man-in-the-middle attack and to make the application believe that the coffee maker really needs an update. And in that case, the user will happily press update the coffee maker and also press the update on the coffee maker itself. So that's one possibility. Obviously, the proximity attack, so you can, as I said, you can be like passing by your neighbor or a company, because these devices also, or these devices, you can find these devices also in companies. And that one which I want to show you is a social engineering attack. That's my favorite one because it doesn't need any special equipment. And then, obviously, you can, for example, sniff the SSID and the password for the network that the coffee maker is being connected to. And the social engineering attack is pretty simple. Just send the packet which starts the update on the coffee maker, and the prompt tells to a user that the coffee maker needs an update and basically asks him to either confirm the update by pressing OK or pressing cancel. But I've tried it on my wife. And if you're sending the packet start update over and over, there is basically no way how you can cancel. Because if you press the cancel, it displays again the update. So after some try, a number of tries, everybody gave up and pressed the update. So that's the simplest social engineering attack you can do. And it turned out also that probably users don't really need a smart coffee makers, because if you go to a Viggo, which is like the database or map of all Wi-Fi networks around the globe, you can easily find like 2,500 coffee makers with the open Wi-Fi that never have been set up. So yes. The question is if we really need a smart coffee maker. So to conclude my talk, the one problem with most IoT devices is so-called out-of-the-box problem. So we have a lot of IoT devices that just works when you basically take them out of the box and connect them. And that's an issue, because for example, my personal experience from the apartment where I moved to is that there was an Ethernet socket for the internet. So I've connected my laptop, and because I'm curious, I was curious what's behind the wall. So I've connected to my default gateway. And it turned out that my default gateway asked me to set up the password for the first time. And that's a problem. That's a problem. Like, these IoT devices, like we've exchanged the convenience for security. That's a really big issue. So we should really make these devices inoperable until you properly set up them. Firmware is no longer firm, but I think this statement is valid for some time already. And the other thing is you need to build the security for the bottom up. So if you are planning to create any IoT device, you should start with the secure OTA update first. Because if you have a secure device on a user level, with a generated username and password, for example, and you have a vulnerable firmware update process, you basically broke the whole security. And the question at the end is, could you really trust any device today? Because this could be a great example of supply chain attack using IoT devices. We've seen this today using a software, using a repositories, but the same thing could be achieved by IoT devices. And the problem is bigger because nobody really knows what's inside the device. OK, so this talk is a memoriam of this device, which is unintentionally bricked. And shortly after this talk, when I get my cup of coffee and some rest, I will upload all the software you've seen and all the documentation for the coffee maker to this GitHub repository. So if you want to download it, just scan the QR code. OK, that's it. I don't know if we have a time for any bonus or Q&A, because there is a bonus.
We can take one or two questions.
Yeah.
Do we have a mic runner?
Hi. It looked like the other ESP pins were soldered in. Did they go anywhere?
Sorry.
So the ESP chip that was soldered onto the motherboard, it looked like that was being, well, more than just the serial pins were soldered to something. Did they actually go anywhere on the traces, or were they just? Yes,
basically from the ESP8266, the pins that had been used were TX, ERIC, so basically RS232 communication pins, and the power. That's basically it. And you can even, like there is a functionality inside the ARM Cortex M0, which allows you to even update the firmware on the ESP8266. But this goes like through the vendor update process, like the vendor of the ESP8266, and it's like known to be pretty secure in this case.
Question over there as well.
Have you been to Own a Coffee yet in Canberra?
Okay, that's a good question.
Owner's actually very good coffee. I like it very much.
Okay, I need to get some coffee, really, and some sleep.
Are there any other questions? One behind the camera over there.
Yeah. Actually, I can show you a little bit of spoiler. This is my upcoming project.
Hello.
Yes.
I was going to suggest that perhaps one of the vendor responses to this convenience versus security thing is to now provide pseudo-secure cloud services whereby your IoT will connect to a vendor-supported cloud service and then you log into that via your phone app. How do you see this as a compromise between security and the control of the device as well as convenience for the operator, user?
It always depends what protocol they use, because that, like in IoT world, is the problem here is that many vendors are using like obscure protocols. It's like a security by obscurity. You don't really know what's inside, and they are basically relying on the fact that if it's unknown and obscure, nobody will like dive into that because nobody understands that protocol, and sometimes it turns out that the protocol is basically a plain text just put into a nice series of bytes. So I think like the communication with cloud is not kind of a proof that the setup is secure. For example, there are light bulbs that are connected to a cloud, and the only identification that they are using when connecting through your Wi-Fi to a cloud is their MAC address. So there is no password, no authorization. The only ID they are using is the MAC address, and the whole protocol, again, is plain text. And it's susceptible to a DOS attack, because if you connect your script to the same cloud with the same identifier, it disconnects the original device, because it can handle only one connection. So I think there is no guarantee that when the configuration is done through a cloud that it's secure. It really depends on the vendor and on the implementation.
Maybe time for one more question. We have one. Well, let's thank Martin for a great talk.
Thank you.